1960s. 1968. Stephen Wiesner invents conjugate coding. Published in ACM SIGACT News 15, 1, 78, 88. 1970s. 1970. James Park articulates the no-cloning theorem. 1973. Alexander Holivo publishes a paper showing that n qubits can carry more than n classical bits of information, but at most n classical bits are accessible, a result known as Holivo's theorem or Holivo's bound. Charles H. Bennett shows that computation can be done reversibly. 1975. R. P. Poplavsky publishes Thermodynamical Models of Information Processing, in Russian, which showed the computational infeasibility of simulating quantum systems on classical computers, due to the superposition principle. 1976. Polish mathematical physicist Roman Stanislaw Ingarden publishes the paper Quantum Information Theory in Reports on Mathematical Physics, Volume 10, 43-72, 1976. The paper was submitted in 1975. It is one of the first attempts at creating a quantum information theory, showing that Shannon information theory cannot directly be generalized to the quantum case, but rather that it is possible to construct a quantum information theory, which is a generalization of Shannon's theory, within the formalism of a generalized quantum mechanics of open systems and a generalized concept of observables, the so-called semi-observables. 1980s. 1980. Paul Benioff describes the first quantum mechanical model of a computer. In this work, Benioff showed that a computer could operate under the laws of quantum mechanics by describing a Schrödinger equation description of Turing machines, laying a foundation for further work in quantum computing. The paper was submitted in June 1979 and published in April 1980. Yuri Manin briefly motivates the idea of quantum computing. Tommaso Toffoli introduces the reversible Toffoli gate, which, together with initialized ancilla bits, is functionally complete for reversible classical computation. 1981. At the first conference on the physics of computation, held at MIT in May, Paul Benioff and Richard Feynman give talks on quantum computing. Benioff's built on his earlier 1980 work showing that a computer can operate under the laws of quantum mechanics. The talk was titled Quantum Mechanical Hamiltonian Models of Discrete Processes That Erase Their Own Histories, Application to Turing Machines. In Feynman's talk, he observed that it appeared to be impossible to efficiently simulate an evolution of a quantum system on a classical computer, and he proposed a basic model for a quantum computer. 1982. Paul Benioff further develops his original model of a quantum mechanical Turing machine. William Wouters and Wojciech Zurek, and independently Dennis Deeks rediscover the no-cloning theorem. 1984. Charles Bennett and Gilles Broussard employ Wiesner's conjugate coding for distribution of cryptographic keys. 1985. David Deutsch, at the University of Oxford, describes the first universal quantum computer. Just as a universal Turing machine can simulate any other Turing machine efficiently, Church-Turing thesis, so the universal quantum computer is able to simulate any other quantum computer with at most a polynomial slowdown. Asher Perez points out need for quantum error correction schemes and discusses a repetition code for amplitude errors. 1988. Yoshihisa Yamamoto and Kei Igita propose the first physical realization of a quantum computer, including Feynman's CNOT gate. Their approach uses atoms and photons and is the progenitor of modern quantum computing and networking protocols using photons to transmit qubits and atoms to perform 2-qubit operations. 1989. Gerard J. Milburn proposes a quantum optical realization of a Fredkin gate. Vikas K. Chakraborty and collaborators from Saha Institute of Nuclear Physics, Kolkata, proposed the idea that quantum fluctuations could help explore rugged energy landscapes by escaping from local minima of glassy systems having tall but thin barriers by tunneling, instead of climbing over using thermal excitations, suggesting the effectiveness of quantum annealing over classical simulated annealing. 1990s. 1991. Artur Occurred at the University of Oxford proposes entanglement-based secure communication. 1992. David Deutsch and Richard Josse propose a computational problem that can be solved efficiently with the determinist Deutsch-Josse algorithm on a quantum computer, but for which no deterministic classical algorithm is possible. This was perhaps the earliest result in the computational complexity of quantum computers, proving that they were capable of performing some well-defined computational task more efficiently than any classical computer. 1993. Dan Simon, at Université de Montréal, invents an oracle problem, Simon's problem, for which a quantum computer would be exponentially faster than a conventional computer. This algorithm introduces the main ideas which were then developed in Peter Shor's factorization algorithm. 1994. Peter Shor, at AT&T's Bell Labs in New Jersey, publishes Shor's algorithm. It allows a quantum computer to factor large integers quickly. It solves both the factoring problem and the discrete log problem. The algorithm can theoretically break many of the cryptosystems in use today. Its invention sparked a tremendous interest in quantum computers. First United States government workshop on quantum computing is organized by NIST in Gaithersburg, Maryland, in autumn. Isaac Chuang and Yoshihisa Yamamoto propose a quantum optical realization of a quantum computer to implement Deutsch's algorithm. Their work introduces dual-rail encoding for photonic qubits. In December, Ignacio Cirac, at University of Castilla-La Mancha at Ciudad Real, and Peter Zoller at the University of Innsbruck propose an experimental realization of the controlled NOT gate with cold trapped ions. 1995. The first United States Department of Defense workshop on quantum computing and quantum cryptography is organized by United States Army physicists Charles M. Bowden, Jonathan P. Dowling, and Henry O. Everett. It takes place in February at the University of Arizona in Tucson. Peter Shor proposes the first schemes for quantum error correction. Christopher Monroe and David Wineland at NIST, Boulder, Colorado, experimentally realize the first quantum logic gate, the controlled NOT gate, with trapped ions, following the Cirac-Zoller proposal. 1996. Lov Grover, at Bell Labs, invents the quantum database search algorithm. The quadratic speedup is not as dramatic as the speedup for factoring, discrete logs, or physics simulations. However, the algorithm can be applied to a much wider variety of problems. Any problem that can be solved by random, brute force search may take advantage of this quadratic speedup in the number of search queries. The United States government, particularly in a joint partnership of the Army Research Office, now part of the Army Research Laboratory, and the National Security Agency, issues the first public call for research proposals in quantum information processing. Andrew Steen designs Steen codes for error correction. David P. DiVincenzo, from IBM, proposes a list of minimal requirements for creating a quantum computer, now called DiVincenzo's criteria. 1997. David Corey, Amr Fahmy, and Timothy Hovell, and at the same time Neil Gershenfeld and Isaac L. Chuang at MIT published the first papers realizing gates for quantum computers based on bulk nuclear spin resonance, or thermal ensembles. The technology is based on a nuclear magnetic resonance (NMR) machine, which is similar to the medical magnetic resonance imaging machine. Alexei Kitaev describes the principles of topological quantum computation as a method for dealing with the problem of decoherence. Daniel Loss and David P. DiVincenzo propose the Loss-DiVincenzo quantum computer, using as qubits the intrinsic spin 1/2 degree of freedom of individual electrons, confined to quantum dots. 1998. First experimental demonstration of a quantum algorithm. A working 2-qubit NMR quantum computer is used to solve Deutsch's problem by Jonathan A. Jones and Michel Mosca at Oxford University, and shortly after by Isaac L. Chuang at IBM's Almaden Research Center and Mark Kubinek and the University of California, Berkeley together with co-workers at Stanford University and MIT. First working 3-qubit NMR computer. Bruce Kane proposes a silicon-based nuclear spin quantum computer, using nuclear spins of individual phosphorus atoms in silicon as the qubits and donor electrons to mediate the coupling between qubits. First execution of Grover's algorithm on an NMR computer. Hideyoshi Nishimori and colleagues from Tokyo Institute of Technology showed that a quantum annealing algorithm can perform better than classical simulated annealing under certain conditions. Daniel Gottesman and Emmanuel Nil independently prove that a certain subclass of quantum computations can be efficiently emulated with classical resources. Gottesman-Nil theorem. 1999. Samuel L. Bronstein and collaborators show that none of the bulk NMR experiments performed to date contained any entanglement, the quantum states being too strongly mixed. This is seen as evidence that NMR computers would likely not yield a benefit over classical computers. It remains an open question, however, whether entanglement is necessary for quantum computational speedup. Gabriel Epley, Thomas Felix Rosenbaum and colleagues demonstrate experimentally the basic concepts of quantum annealing in a condensed matter system. Yasunobue Nakamura and Joshin Tsai demonstrate that a superconducting circuit can be used as a qubit. 2000s. 2000. Arun K. Patti and Samuel L. Bronstein proved the quantum no-deleting theorem. This is dual to the no-cloning theorem, which shows that one cannot delete a copy of an unknown qubit. Together with the stronger no-cloning theorem, the no-deleting theorem has important implication, i.e., quantum information can neither be created nor be destroyed. First working 5-qubit NMR computer demonstrated at the Technical University of Munich. First execution of order finding, part of Shor's algorithm, at IBM's Almaden Research Center and Stanford University. First working 7-qubit NMR computer demonstrated at the Los Alamos National Laboratory. The standard textbook, Quantum Computation and Quantum Information, by Michael Nielsen and Isaac Chuang is published. 2001. First execution of Shor's algorithm at IBM's Almaden Research Center and Stanford University. The number 15 was factored using 1018 identical molecules, each containing 7 active nuclear spins. Noah Linden and Sandu Popescu proved that the presence of entanglement is a necessary condition for a large class of quantum protocols. This, coupled with Bronstein's result, see 1999 above, called the validity of NMR quantum computation into question. Emmanuel Nil, Raymond Laflamme, and Gerard Milburn show that optical quantum computing is possible with single photon sources, linear optical elements, and single photon detectors, launching the field of linear optical quantum computing. Robert Rossendorf and Hans-Jürgen Briegel proposed measurement-based quantum computation. 2002. The Quantum Information Science and Technology Roadmapping Project, involving some of the main participants in the field, laid out the quantum computation roadmap. The Institute for Quantum Computing was established at the University of Waterloo in Waterloo, Ontario, by Mike Lazaridis, Raymond Laflamme and Michel Mosca. 2003. Implementation of the Deutsche Jasa algorithm on an ion-trap quantum computer at the University of Innsbruck. Todd D. Pittman and collaborators at Johns Hopkins University, Applied Physics Laboratory and independently Jeremy L. O'Brien and collaborators at the University of Queensland, demonstrate quantum-controlled NOT gates using only linear optical elements. First implementation of a CNOT quantum gate according to the Sirac-Zoller proposal by a group at the University of Innsbruck led by Rainer Blatt. DARPA Quantum Network becomes fully operational on October 23, 2003. The Institute for Quantum Optics and Quantum Information, ICOQI, was established in Innsbruck and Vienna, Austria, by the founding directors Rainer Blatt, Hans-Jürgen Briegel, Rudolf Grimm, Anton Zeilinger and Peter Zoller. 2004. First working pure-state NMR quantum computer, based on parahydrogen, demonstrated at Oxford University and University of York. Physicists at the University of Innsbruck show deterministic quantum state teleportation between a pair of trapped calcium ions. First 5-photon entanglement demonstrated by Jianwei Pan's group at the University of Science and Technology of China, the minimal number of qubits required for universal quantum error correction. 2005. University of Illinois at Urbana-Champaign scientists demonstrate quantum entanglement of multiple characteristics, potentially allowing multiple qubits per particle. Two teams of physicists measured the capacitance of a Josephson junction for the first time. The methods could be used to measure the state of quantum bits in a quantum computer without disturbing the state. In December, W states of quantum registers with up to 8 qubits implemented using trapped ions are demonstrated at the Institute for Quantum Optics and Quantum Information and the University of Innsbruck in Austria. Harvard University and Georgia Institute of Technology researchers succeeded in transferring quantum information between quantum memories, from atoms to photons and back again, citation needed. 2006. Material Science Department of Oxford University, cage a qubit in a buckyball, a molecule of Buckminster fullerene, and demonstrated quantum bang-bang error correction. Researchers from the University of Illinois at Urbana-Champaign use the Zeno effect, repeatedly measuring the properties of a photon to gradually change it without actually allowing the photon to reach the program, to search a database without actually running the quantum computer. Vlatko Vedral of the University of Leeds and colleagues at the Universities of Porto and Vienna found that the photons in ordinary laser light can be quantum mechanically entangled with the vibrations of a macroscopic mirror. Samuel L. Bronstein at the University of York along with the University of Tokyo and the Japan Science and Technology Agency gave the first experimental demonstration of quantum telecloning. Professors at the University of Sheffield develop a means to efficiently produce and manipulate individual photons at high efficiency at room temperature. New error-checking method theorized for Josephson junction computers. First 12-qubit quantum computer benchmarked by researchers at the Institute for Quantum Computing and the Perimeter Institute for Theoretical Physics in Waterloo, as well as MIT, Cambridge. Two-dimensional ion trap developed for quantum computing. 7 atoms placed in stable line, a step on the way to constructing a quantum gate, at the University of Bonn. A team at Delft University of Technology in the Netherlands created a device that can manipulate the up or down spin states of electrons on quantum dots. University of Arkansas develops quantum dot molecules. Spinning new theory on particle spin brings science closer to quantum computing. University of Copenhagen develops quantum teleportation between photons and atoms. University of Camerino scientists develop theory of macroscopic object entanglement, which has implications for the development of quantum repeaters. Taichung Chang, at Illinois at Urbana-Champaign, finds that quantum coherence can be maintained in mixed material systems. Christophe Bohm, University of Utah, demonstrates the feasibility of reading spin data on a silicon phosphorus quantum computer. 2007. Subwavelength waveguide developed for light. Single photon emitter for optical fibers developed. 6-photon one-way quantum computer is created in lab. New material proposed for quantum computing. Single-atom single-photon server devised. First use of Deutsch's algorithm in a cluster-state quantum computer. University of Cambridge develops electron quantum pump. Superior method of qubit coupling developed. Successful demonstration of controllably coupled qubits. Breakthrough in applying spin-based electronics to silicon. Scientists demonstrate quantum state exchange between light and matter. Diamond quantum register developed. Controlled not quantum gates on a pair of superconducting quantum bits realized. Scientists study hundreds of individual atoms in 3D array. Nitrogen in buckyball molecule used in quantum computing. Large number of electrons quantum coupled. Spin-orbit interaction of electrons measured. Atoms quantum manipulated in laser light. Light pulses used to control electron spins. Quantum effects demonstrated across tens of nanometers. Light pulses used to accelerate quantum computing development. Quantum RAM blueprint unveiled. Model of quantum transistor developed. Long-distance entanglement demonstrated. Photonic quantum computing used to factor number by 2 independent labs. Quantum bus developed by two independent labs. Superconducting quantum cable developed. Transmission of qubits demonstrated. Superior qubit material devised. Single electron qubit memory. Bose-Einstein condensate quantum memory developed. D-Wave Systems demonstrates use of a 28-qubit quantum annealing computer. New cryonic method reduces decoherence and increases interaction distance, and thus quantum computing speed. Photonic quantum computer demonstrated. Graphene quantum dot spin qubits proposed. 2008. The HHL algorithm for solving linear equations was published. Graphene quantum dot qubits. Quantum bit stored. 3D qubit Qtrid entanglement demonstrated. Analog quantum computing devised. Control of quantum tunneling. Entangled memory developed. Superior NOT gate developed. Qtrits developed. Quantum logic gate in optical fiber. Superior quantum Hall effect discovered. Enduring spin states in quantum dots. Molecular magnets proposed for quantum RAM. Quasiparticles offer hope of stable quantum computer. Image storage may have better storage of qubits. Quantum entangled images. Quantum state intentionally altered in molecule. Electron position controlled in silicon circuit. Superconducting electronic circuit pumps microwave photons. Amplitude spectroscopy developed. Superior quantum computer test developed. Optical frequency comb devised. Quantum Darwinism supported. Hybrid qubit memory developed. Qubit stored for over 1 second in atomic nucleus. Faster electron spin qubit switching and reading developed. Possible non-entanglement quantum computing. D-Wave Systems claims to have produced a 128-qubit computer chip, though this claim has yet to be verified. 2009. Carbon-12 purified for longer coherence times. Lifetime of qubits extended to hundreds of milliseconds. Quantum control of photons. Quantum entanglement demonstrated over 240 micrometers. Qubit lifetime extended by factor of 1000. First electronic quantum processor created. 6-photon graph state entanglement used to simulate the fractional statistics of anyons living in artificial spin lattice models. Single molecule optical transistor. NIST reads, writes individual qubits. NIST demonstrates multiple computing operations on qubits. First large-scale topological cluster state quantum architecture developed for atom optics. A combination of all of the fundamental elements required to perform scalable quantum computing through the use of qubits stored in the internal states of trapped atomic ions shown. Researchers at University of Bristol demonstrate Shor's algorithm on a silicon photonic chip. Quantum computing with an electron spin ensemble. Photon machine gun developed for quantum computing. First universal programmable quantum computer unveiled. Scientists electrically control quantum states of electrons. Google collaborates with D-Wave Systems on image search technology using quantum computing. A method for synchronizing the properties of multiple coupled CJJ-RF squid flux qubits with a small spread of device parameters due to fabrication variations was demonstrated. Realization of universal ion trap quantum computation with decoherence-free qubits. First chip-scale quantum computer. 2010s. 2010. Ion trapped in optical trap. Optical quantum computer with 3 qubits calculated the energy spectrum of molecular hydrogen to high precision. First germanium laser brings us closer to optical computers. Single electron qubit developed. Quantum state in macroscopic object. New quantum computer cooling method developed. Racetrack ion trap developed. Evidence for a Moore-Reed state in the U equals 5/2 quantum Hall plateau, which would be suitable for topological quantum computation. Quantum interface between a single photon and a single atom demonstrated. LED quantum entanglement demonstrated. Multiplex design speeds up transmission of quantum information through a quantum communications channel. 2-photon optical chip. Microfabricated planar ion traps. Boson sampling technique proposed by Aronson and Arkhipov. Quantum dot qubits manipulated electrically, not magnetically. 2011. Entanglement in a solid-state spin ensemble. Neon photons in superconducting quantum integrated circuit. Quantum antenna. Multimode quantum interference. Magnetic resonance applied to quantum computing. Quantum pen. Atomic racing duel. 14-qubit register. D-Wave claims to have developed quantum annealing and introduces their product called D-Wave 1. The company claims this is the first commercially available quantum computer. Repetitive error correction demonstrated in a quantum processor. Diamond quantum computer memory demonstrated. Modes developed. Decoherence suppressed. Simplification of controlled operations. Ions entangled using microwaves. Practical error rates achieved. Quantum computer employing von Neumann architecture. Quantum spin Hall topological insulator. Two diamonds linked by quantum entanglement could help develop photonic processors. 2012. D-Wave claims a quantum computation using 84 qubits. Physicists create a working transistor from a single atom. A method for manipulating the charge of nitrogen vacancy centers in diamond. Reported creation of a 300-qubit particle quantum simulator. Demonstration of topologically protected qubits with an 8-photon entanglement, a robust approach to practical quantum computing. 1QB Information Technologies, 1qubit, founded. World's first dedicated quantum computing software company. First design of a quantum repeater system without a need for quantum memories. Decoherence suppressed for 2 seconds at room temperature by manipulating carbon-13 atoms with lasers. Theory of Bell-based randomness expansion with reduced assumption of measurement independence. New low-overhead method for fault-tolerant quantum logic developed, called lattice surgery. 2013. Coherence time of 39 minutes at room temperature and 3 hours at cryogenic temperatures, demonstrated for an ensemble of impurity spin qubits in isotopically purified silicon. Extension of time for qubit maintained in superimposed state for 10 times longer than what has ever been achieved before. First resource analysis of a large-scale quantum algorithm using explicit fault-tolerant, error correction protocols was developed for factoring. 2014. Documents leaked by Edward Snowden confirm the Penetrating Hard Targets project, by which the National Security Agency seeks to develop a quantum computing capability for cryptography purposes. Researchers in Japan and Austria published the first large-scale quantum computing architecture for a diamond-based system. Scientists at the University of Innsbruck do quantum computations on a topologically encoded qubit which is encoded in entangled states distributed over 7 trapped ion qubits. Scientists transfer data by quantum teleportation over a distance of 10 feet, 3.048 meters, with 0% error rate, a vital step towards a quantum internet. 2015. Optically addressable nuclear spins in a solid with a 6-hour coherence time. Quantum information encoded by simple electrical pulses. Quantum error detection code using a square lattice of 4 superconducting qubits. D-Wave Systems Incorporated announced on June 22 that it had broken the 1,000-qubit barrier. A 2-qubit silicon logic gate is successfully developed. A quantum computer, along with quantum superposition and entanglement, is emulated by a classical analog computer, with the result that the fully classical system behaves like a true quantum computer. 2016. Physicists led by Rainer Blatt joined forces with scientists at MIT, led by Isaac Chuang, to efficiently implement Shor's algorithm in an ion trap-based quantum computer. IBM releases the Quantum Experience, an online interface to their superconducting systems. The system is immediately used to publish new protocols in quantum information processing. Google, using an array of 9 superconducting qubits developed by the Martinis Group and UCSB, simulates a hydrogen molecule. Scientists in Japan and Australia invent the quantum version of a sneakernet communications system. 2017. D-Wave Systems Incorporated announces general commercial availability of the D-Wave 2000Q quantum annealer, which it claims has 2000 qubits. Blueprint for a microwave trapped ion quantum computer, published. IBM unveils 17-qubit quantum computer, and a better way of benchmarking it. Scientists build a microchip that generates 2 entangled qubits each with 10 states, for 100 dimensions total. Microsoft reveals Q hashtag, a quantum programming language integrated with Visual Studio. Programs can be executed locally on a 32-qubit simulator, or a 40-qubit simulator on Azure. Rubaiyat Hossain, OMI, the former Intelligent Systems Advisor of DARPA in collaboration with the researchers of Quail, developed the world's first user-interactive operating system to be used in commercial quantum computers. And Intel confirms development of a 17-qubit superconducting test chip. IBM reveals a working 50-qubit quantum computer that can maintain its quantum state for 90 microseconds. First teleportation using a satellite, connecting ground stations over a distance of 1,400 kilometers apart. Previous experiments was at Earth, at shorter distances. 2018. MIT scientists report the discovery of a new triple photon form of light. Oxford researchers successfully use a trapped ion technique, where they place 2 charged atoms in a state of quantum entanglement to speed up logic gates by a factor of 20 to 60 times, as compared with the previous best gates, translated to 1.6 microseconds long, with 99.8% precision. ChuTech successfully tests a silicon-based 2-spin qubit processor. Google announces the creation of a 72-qubit quantum chip, called Bristlecone, achieving a new record. Intel begins testing a silicon-based spin-qubit processor manufactured in the company's D1D fab in Oregon. Intel confirms development of a 49-qubit superconducting test chip, called Tango Lake. Japanese researchers demonstrate universal holonomic quantum gates. Integrated photonic platform for quantum information with continuous variables. On December 17, 2018, the company IonQ introduced the first commercial trapped ion quantum computer, with a program length of over 62-qubit gates, 11 fully connected qubits, 55 addressable pairs, 1-qubit gate error less than 0.03% and 2-qubit gate error less than 1%. On December 21, 2018, the National Quantum Initiative Act was signed into law by President Donald Trump, establishing the goals and priorities for a 10-year plan to accelerate the development of quantum information science and technology applications in the United States. 2019. IBM Q System 1, 2019, the first circuit-based commercial quantum computer. See also, 2019 in Science. IBM unveils its first commercial quantum computer, the IBM Q System 1, designed by UK-based MAP Project Office and Universal Design Studio, and manufactured by Goppian. Austrian physicists demonstrate self-verifying, hybrid, variational quantum simulation of lattice models in condensed matter and high-energy physics using a feedback loop between a classical computer and a quantum coprocessor. Quantum Darwinism observed in diamond at room temperature. A paper by Google's quantum computer research team was briefly available in late September 2019, claiming the project has reached quantum supremacy. IBM reveals its biggest quantum computer yet, consisting of 53 qubits. The system goes online in October 2019. University of Science and Technology of China researchers demonstrate boson sampling with 14 detected photons. 2020s. 2020. See also, 2020 in Science, Timeline of Computing 2020-Present, and 2020 in Philosophy. UNSW Sydney develops a way of producing hot qubits, quantum devices that operate at 1.5 kelvins, when Griffith University, UNSW, and UTS, in partnership with 7 universities in the United States, develop noise cancelling for quantum bits via machine learning, taking quantum noise in a quantum chip down to 0%. UNSW performs electric nuclear resonance to control single atoms in electronic devices, when University of Tokyo and Australian scientists create and successfully test a solution to the quantum wiring problem, creating a 2D structure for qubits. Such structure can be built using existing integrated circuit technology and has a considerably lower crosstalk. When January 16, quantum physicists report the first direct splitting of one photon into three using spontaneous parametric downconversion and which may have applications in quantum technology. February 11, quantum engineers report that they have created artificial atoms in silicon quantum dots for quantum computing and that artificial atoms with a higher number of electrons can be more stable qubits than previously thought possible. Enabling silicon-based quantum computers may make it possible to reuse the manufacturing technology of classical modern-day computer chips among other advantages. February 14, quantum physicists develop a novel single-photon source which may allow to bridge semiconductor-based quantum computers that use photons by converting the state of an electron spin to the polarization of a photon. They show that they can generate a single photon in a controlled way without the need for randomly formed quantum dots or structural defects in diamonds. February 25, scientists visualize a quantum measurement by taking snapshots of ion states at different times of measurement by a coupling of a trapped ion qubit to the photon environment. They show that the changes of the degrees of superpositions and therefore probabilities of states after measurement happens gradually under the measurement influence. March 2, scientists report to have achieved repeated quantum non-demolition measurements of an electron spin in a silicon quantum dot. Measurements that don't change the electron spin in the process. March 11, quantum engineers report to have managed to control the nucleus of a single atom using only electric fields. This was first suggested to be possible in 1961 and may be used for silicon quantum computers that use single-atom spins without needing oscillating magnetic fields, which may be especially useful for nanodevices, for precise sensors of electric and magnetic fields as well as for fundamental inquiries into quantum nature. March 19, a U.S. Army laboratory announces that its scientists analyzed a Rydberg sensor's sensitivity to oscillating electric fields over an enormous range of frequencies, from 0 to 10 to the power of 12 Hz, the spectrum to 0.3 mm wavelength. The Rydberg sensor may potentially be used to detect communication signals as it could reliably detect signals over the entire spectrum and compare favorably with other established electric field sensor technologies, such as electro-optic crystals and dipole antenna-coupled passive electronics. March 23, researchers report that they have found a way to correct for signal loss in a prototype quantum node that can catch, store, and entangle bits of quantum information. Their concepts could be used for key components of quantum repeaters in quantum networks and extend their longest possible range. April 15, researchers demonstrate a proof-of-concept silicon quantum processor unit cell, which works at 1.5 kelvins, many times warmer than common quantum processors that are being developed. It may enable integrating classical control electronics with the qubit array and reduce costs substantially. The cooling requirements necessary for quantum computing have been called one of the toughest roadblocks in the field. April 16, scientists prove the existence of the Rashba effect in bulk perovskites. Previously, researchers have hypothesized that the material's extraordinary electronic, magnetic, and optical properties, which make it a commonly used material for solar cells and quantum electronics, are related to this effect, which to date hasn't been proven to be present in the material. May 8, researchers report to have developed a proof of concept of a quantum radar using quantum entanglement and microwaves, which may potentially be useful for the development of improved radar systems, security scanners, and medical imaging systems. May 12, researchers report to have developed a method to selectively manipulate a layered manganite's correlated electron spin state while leaving its orbital state intact using femtosecond X-ray laser pulses. This may indicate that orbitronics, using variations in the orientations of orbitals, may be used as the basic unit of information in novel IT devices. May 19, researchers report to have developed the first integrated silicon on-chip low-noise single-photon source compatible with large-scale quantum photonics. June 11, scientists report the generation of rubidium bows, Einstein condensates, BECS, in the Cold Atom Laboratory aboard the International Space Station under microgravity, which could enable improved research of BECS and quantum mechanics, whose physics are scaled to macroscopic scales in BECS, support long-term investigations of few-body physics, support the development of techniques for atom wave interferometry and atom lasers, and has verified the successful operation of the laboratory. June 15, scientists report the development of the smallest synthetic molecular motor, consisting of 12 atoms and a rotor of 4 atoms, shown to be capable of being powered by an electric current using an electron scanning microscope and moving even with very low amounts of energy due to quantum tunneling. June 17, quantum scientists report the development of a system that entangles 2-photon quantum communication nodes through a microwave cable that can send information in between without the photons ever being sent through, or occupying, the cable. On June 12 it was reported that they also, for the first time, entangled 2 phonons as well as erase information from their measurement after the measurement has been completed using delayed choice quantum erasure. August 13, universal coherence protection is reported to have been achieved in a solid-state spin qubit, a modification that allows quantum systems to stay operational, or coherent, for 10,000 times longer than before. August 26, scientists report that ionizing radiation from environmental radioactive materials and cosmic rays may substantially limit the coherence times of qubits if they aren't shielded adequately. August 28, quantum engineers working for Google report the largest chemical simulation on a quantum computer, a Hartree-Fock approximation with Sycamore paired with a classical computer that analyzed results to provide new parameters for the 12-qubit system. September 2, researchers present an 8-user city-scale quantum communication network, located in Bristol, using already deployed fibers without active switching or trusted nodes. September 21, researchers report the achievement of quantum entanglement between the motion of a millimeter-sized mechanical oscillator and a disparate distance spin system of a cloud of atoms. December 3, Chinese researchers claim to have achieved quantum supremacy, using a photonic peak 76-qubit system, 43 average, known as Jiuzhong, which performed calculations at 100 trillion times the speed of classical supercomputers. December 21, publication of research of counterfactual quantum communication, whose first achievement was reported in 2017, by which information can be exchanged without any physical particle traveling between observers and without quantum teleportation. The research suggests that this is based on some form of relation between the properties of modular angular momentum. 2021. January 6, Chinese researchers report that they have built the world's largest integrated quantum communication network, combining over 700 optical fibers with 2 QKD ground-to-satellite links for a total distance between nodes of the network of networks of up to 600 km. January 13, Austrian researchers report the first realization of an entangling gate between 2 logical qubits encoded in topological quantum error correction codes using a trapped ion quantum computer with 10 ions. January 15, researchers in China report the successful transmission of entangled photons between drones, used as nodes for the development of mobile quantum networks or flexible network extensions, marking the first work in which entangled particles were sent between 2 moving devices. January 28, Swiss and German researchers report the development of a highly efficient single-photon source for quantum IT with a system of gated quantum dots in a tunable microcavity which captures photons released from these excited artificial atoms. February 5, researchers demonstrate a first prototype of quantum logic gates for distributed quantum computers. April 13, in a preprint, an astronomer describes for the first time how one could search for quantum communication transmissions sent by extraterrestrial intelligence using existing telescope and receiver technology. He also provides arguments for why future searches of SETI should also target interstellar quantum communications. May 7, Two studies complement research published September 2020, see item, by quantum entangling two mechanical oscillators. June 8, a Japanese tech company achieves quantum communications over optical fibers exceeding 600 kilometers in length, a new world record distance. June 17, Austrian, German, and Swiss researchers present a 219-inch rack quantum computing demonstrator, the world's first quality standards meeting compact quantum computer. July 7, American researchers present a programmable quantum simulator that can operate with 256 qubits, and on the same date and journal another team presented quantum simulator of 196 Rydberg atoms trapped in optical tweezers. October 25, Chinese researchers reported that they have developed the world's fastest programmable quantum computers. The photon-based Jiuzhong 2 is claimed to be able to calculate a task in 1 millisecond that would otherwise have taken a conventional computer 30 trillion years to complete. And Zhongzi 2 is a 66-qubit programmable superconducting quantum computer that is claimed to be the current world's fastest quantum computer that can run a calculation task 1 million times more complex than Google's Sycamore, as well as being 10 million times faster. See also, Quantum Supremacy, Progress in the 21st Century. November 11, the first simulation of baryons on a quantum computer is reported by University of Waterloo. November 16, IBM claims that it has created a new 127 quantum bit processor, IBM Eagle, which according to a report is the most powerful quantum processor known. According to the report, the company has not yet published an academic paper describing its metrics, performance, or abilities. 2022. January 18, Europe's first quantum annealer with more than 5,000 qubits is launched in Jülich, Germany. March 24, the first prototype, photonic, quantum memoristive device, for neuromorphic, quantum, computers and artificial neural networks, that is able to produce memoristive dynamics on single photon states through a scheme of measurement and classical feedback is invented. April 14, the Quantinuum system model H1-2 doubled its performance, claiming to be the first commercial quantum computer to pass quantum volume 4096. June 22, the world's first quantum computer integrated circuit is demonstrated. June 28, physicists report that interstellar quantum communication by other civilizations could be possible and may be advantageous, identifying some potential challenges and factors for detecting such. They may use, for example, X-ray photons for remotely established quantum communications and quantum teleportation as the communication mode. August 15, Nature Materials publishes the first work showing optical initialization and coherent control of nuclear spin qubits in 2D materials, an ultra-thin hexagonal boron nitride. August 24, Nature publishes the first research related to a set of 14 photons entangled with high efficiency and in a defined way. August 26, created photon pairs at several different frequencies using optical ultra-thin resonant metasurfaces made up of arrays of nanoresonators. August 29, researchers generated up to 14 stable photons in an optical resonator nearly half the time and through a scalable and freely programmable source. August 29, physicists at the Max Planck Institute entangled 14 photons together, starting from an atom of rubidium, trapped in an optical cavity that bounces electromagnetic waves around in certain patterns. September 2, researchers from the University of Tokyo and other Japanese institutions developed a systematic method that applies optimal control theory, GRAPE algorithm, to identify the theoretically optimal sequence from among all conceivable quantum operation sequences. It is necessary to complete the operations within the time that the coherent quantum state is maintained. September 30, researchers at University of New South Wales achieved a coherence time of 2 milliseconds, 100 times higher than the previous benchmark in the same quantum processor.